As geographers, we are interested in how landscapes are shaped and change over time. Many changes within a landscape occur rapidly and with a magnitude that makes them immediately visible. A storm on a beach can transport considerable volumes of sand. But what happens in between? Would you believe that under quite sunny conditions, similar volumes of sand can also be transported through wind and wave action? The surface of our Earth is continuously shaped by natural processes, with different event magnitudes, velocities, and frequencies. With terrestrial laser scanning, we can obtain a detailed three-dimensional snapshot of the topography at a point in time. When the scanning is repeated, as on the snow-covered slope, the surface change between acquisitions can be derived. From this change image, we can interpret that the overall snow cover decreased, but the surface height increased where avalanches occurred and deposited snow. But there's also a lot we cannot tell. When exactly did the avalanches occur? Did the snow cover melt away continuously, or was there snowfall in between? How changes to a landscape evolved can be captured by the recent strategy of near-continuous TLS.
In near-continuous TLS, the scanner is installed in a fixed position and set to automatically repeat the acquisition at regular intervals. These are powerful data sets where we capture many occurrences of rapid change as well as slower changes. An important aspect is we also get more information that was not recorded before. The history of surface change tells us how it evolved over time and maybe changed its shape, its position, and also its extent. This can often not be interpreted from a single snapshot. Think of the 3D point cloud like a photo that you take of a scene, and how much more you could see in a time lapse, almost like a movie.
This is what near-continuous TLS of a sandy beach may look like. The scanner overlooks the beach and acquires data, say every half hour. What it records over time is the volume change of the surface through accumulation and erosion of sand that is transported by wind, waves, and also by anthropogenic influence. Surface changes of different magnitudes and velocities are captured over different areas of the beach. These temporal properties themselves define the level of detail that we may wish to monitor at, both in terms of the spatial and temporal resolution.
Automatically adapting the observation to the current changes in the scene is a key idea of the Auto3Dscapes project. We want to acquire data only when and where changes occur. This first requires us to automatically detect the many different types of changes that potentially occur in the data. To realize this, we are developing advanced methods of change analysis. The first improvement is that we are no longer only looking at the change image between 2 points in time. By including the full temporal domain, our algorithm can automatically identify an area that has a similar history of surface change. Based on this video, we can interpret much better how the surface change developed over time.
Continuing this research, the Auto3Dscapes project will enable autonomous 3D Earth observation to monitor and then further understand Earth-shaping processes in different landscapes.